Okay. Today, the plan is to continue our discussion of probability theory. And depending on how far we get, extend from probability to statistics. All right. Now let's get back to the notation of probability theory. And so this will always start with the once upon a time of the fable told by probability theorists, which is let omega f p be a probability space. If you read papers in probability theory, they all start like this, in the same way that if you read a fairy tale, they start with once upon a time. And so this is a good place to begin again. Now, where we left off was we described what a probability space is. We mentioned that there's a set, which is the space of possible things that can happen. And then there's a collection of sets known as the sigma field or the sigma algebra, which is all of the subsets of the collection of things that can happen that we can make statements about. And so this will not always be uniquely defined. We need to define which is the set of subsets that we're interested in. And it corresponds to the information that we have about the subsets of this space. And then a probability assigns to each of these subsets a weight that says this one is more likely or less likely. And so each of these satisfy a set of axioms of the kinds of subsets that have to be included in a sigma algebra and the properties of a probability. In particular, it's a map from F to the non-negative numbers between 0 and 1, and it's it assigns to the empty set a probability 0. It assigns to the full space omega a probability 1, and then if you have two disjoint sets, the probability of the union of those sets is equal to the sum of the probabilities. Now, we left off with random variables. And so a random variable is just a function that's defined on a probability space. So we denote this with sometimes omega to denote that the arguments of this function are elements of the probability space big omega. And we associate this not just with omega, but because this probability space is equipped with a sigma algebra and a probability, this is actually, so this is a function from omega and f with probability p, and it's measurable. So this is from omega comma f to a space X. And then we actually need to, when we're describing this, equip the set X with its own sigma field. And so we say X is measurable, which is shorthand for X is omega f to bracket x, curly x measurable if for any b in the range space, then x inverse b, which is defined as the set of omega such that x omega is in B, is in F. And so that just says that the function has to be defined for any outcome that you're interested in describing, defined with respect to the information in your information set. And so we can think about this. If it's a decision an individual is making, it has to be a decision based on the information they have. They can't distinguish between, for example, subsets of sets that are not in their information set F. And so this is rather tedious notation, always having to specify so both the original sigma field in the domain space and the range and sigma field in the range space. It's very often going to be the case that we're not even going to state those when we mention a random variable, and we'll let it be inferred from context. Indeed, you'll note that when I wrote x, I got rid of the function of omega here. Often with random variables, we omit that piece of notation. So it always is a function of whatever the underlying probability space is. But extremely often when you're working with probability, it won't be specified in that way. You'll just see an x and it will be stated that it's a random variable. And often the specific probability space on which it's defined will be left purely implicit. Likewise, the range space. Usually you can use some kind of natural or obvious range space, sigma field over the range space. For example, if this is a function between topological spaces, which is it's a little bit more structure than just a set, but not much. It says that there exist subsets that have this property called being open. Then we can define the Borel sigma field, which is the sigma field that contains all the open sets. And so often that's sort of going to be left implicit. And when we say, x of omega is omega times 2, where omega might be a real number. So then the range is a real number, and then it's very often going to be the case that within the real numbers, the sigma field that we're going to be using is the Borel sigma field that assigns to these intervals measurability. Now, the interesting thing about random variables on probability spaces is not so much the sigma fields. We need those to be defined, but the probabilities themselves. And so we have a space and a sigma field for the range. And so that suggests we might want a probability distribution. We already have a probability measure for the domain space. And it turns out that once we have that, and once we have a random variable, that defines another probability measure. So we define, let me fix this, define probability measure. I'm going to denote this P sub x on x curly x. as the measure satisfying the measure of any set B with respect to this probability measure Px is equal to the probability on the original space that this function x omega is in B. So this probability is defined as it's defined over sets in the sigma field F. And we note that this probability that X is in B is simply equal to the probability of this set X inverse B here, which by measurability is an element of the sigma field F. And so it's something over which we can define a probability. And so that says we don't need an additional probability measure. We can define a new probability measure through a function. And we call this Px the distribution of the random variable x. And so very often we'll only define a single probability measure, and then there's going to be many functions we'll define a single probability space, and then there's going to be many functions defined over it. And the probability measures over the spaces on which they live will then be defined purely by this process. So sometimes we call this the push forward measure on X. So if you're talking to measure theorists, they'll say push forward. If you're talking to probabilists or most anybody who applies probability, they'll say distribution. But just the idea push forward conveys this idea that it maps the probability from one space to another space. So from omega f to x. And so what can we do with random variables? Lots of things. Now we can define relationships between objects. A particular useful thing that we can do with a probability measure and a random variable is define its expectation. And so this is sometimes also called the mean of a random variable or the average of a random variable. And sometimes that's specialized to population average in statistics to distinguish it from other types of averages like just the finite sum. And so what is this? This is for each P on omega F, there is a map on the space of random variables which we denote this E with an extra line, the expectation. And we'll define this in the same way we've been defining previous terms, axiomatically. We'll characterize it by a set of properties that, that uniquely define what this expectation is. So, so properties of an expectation, these are axioms, in fact. These are defining properties. The first is that, so we have now that the expectation of a particular class of random variables, the indicator functions, is equal to the probability of that set, the set for which they're an indicator. So recall that an indicator function, so indicator of omega in A is a function which equals 1 if omega is in A, and 0 if omega is not in A. So it's just a 0, 1 valued function. And for those functions, the average of that function is just equal to the probability of the set over which it's defined. And that's true for any A in the set F over which a probability can be defined. So that tells us that essentially the size of that set, this probability is equal to, so that average times 1. The next property, again, 0 is special. Expectation of 0 equals 0. This could actually be derived from the indicator of the empty set is always equal to 0. And the probability of the empty set is also equal to 0 axiomatically. The next condition is linearity. So if this were only definable over indicator variables, it would not be very useful because it would just be equal to probability. But we can now take any random variables, x and y, and any real numbers, a and b, and the random variable defined by the sum of two random variables, or the weighted sum, is equal to the sum has an expectation equal to the sum of the weighted sum of the expectations for any a and b that are real numbers, and any x and y that are random variables. And so this allows us to combine random variables. So starting with, for example, these indicator variables, we can multiply them by a number. We can multiply this by 2 and say, or 3 or 4 or whatever. And so we have then, for example, that the expectation of 3 times the indicator variable of a set is 3 times the probability of that set. And so we can think about this as the probability of the set defines the size, the width, and then that gets multiplied by the height to define an area. And so the expectation can be thought about as an area geometrically when we do this. And we can extend this beyond these linear combinations using, so sometimes this is defined as an axiom. Sometimes people use other axioms. To define this, and state this as a theorem. But this is what's known as the monotone convergence property. And it says what happens as you take limits. So for a sequence, x1 omega, x2 omega, and so on up through some arbitrary number, so a countable sequence of random variables, such that 0 is less than or equal to x1 of omega, is less than or equal to x2 of omega, is less than or equal to, and so on. So this is an increasing sequence. So at every value omega, the value of the random variable is weakly increasing. And if these converge in this monotone fashion to some limit, which we'll call x omega, for every omega in the domain omega, then expectation of the limit object, or let's say, so the here, let's do this the other way. Then the limit as I goes to infinity of the expectations of the sequence converge to the expectation of the limit object x omega, or more succinctly, limit of expectation of xi is equal to the expectation of the limit of xi. And so that says we can interchange expectations and limits, but it only for monotone increasing non-negative sequences of random variables. So what this allows us to do is define for essentially any function of interest an expectation. And the way we perform this calculation will look both a little familiar and a little strange to somebody who's taken a basic calculus class. So this is a way of computing area, but it's slightly different from other ways of computing area that you've seen. So let me draw a diagram. So here's our space omega. Okay, didn't realize that the software let us draw straight lines like that. It's nice. So here's our space omega. And then consider some function on the space omega. Let's call this x omega, for which we want to know the expectation. So maybe it looks like this, some arbitrary function, drawn it in this way. And now, how do we calculate the expectation of this function using these axioms? So we can rely on the indicator variables. Those are ones which we know the measure of. We can rely on linear combinations of those variables, and we can rely on taking monotone limits. So what does this allow us to do? We can start by, so consider a set like this. So this is some set in omega. And it has some measure. So let's call this set A. And the measure of that set is probability of A. If we take an indicator variable, so that's a variable of height 1, then, so let's say this right here is, this right here is 1, a variable of height 1, then the measure of this is 1. We can, by linearity, extend this further up to whatever this height here is at this point. Maybe these hit, maybe these don't hit at 2 places. And so this is the height. So this is, let's say, little a. And then the area of this term of this object is little a times probability of a. And so that, notice that we kept this below. What we can do from this is cover up the space with indicator variables of sets, just like that, kept below. So maybe this is 1, this is another. These don't have to be regular in any way, they just have to be measurable sets is the only requirement. And so on. I'm not going to draw all of these. And just cover this. And we know the area of each of these sets. We've defined it through axiom 1 and axiom 3. And now, in order to reach the limit, we can say, well, we're still below, but what we can do is we can come up with subsets of these sets. And so here's another subset that's narrower, and extend this up here. So we've split this subset. And then supposing this is measurable, the intersection and complement are also in the sigma field. So this is some set B. And then if we take this little set, then these sets are also measurable. And so these heights are, these widths are still defined. And these heights are the same, and we can increase the height. And we can do that. And so for each of these variables, we can subdivide them, each of these components, and we can subdivide them. And then we get now a function that maps a more fine partition of the space. And it's closer, but still below. And we can keep on doing this. And so we've added, now in doing that, we've added the area in each of these little components to that. We can keep on doing that. We can take the limit. So long as that limit is monotone increasing by the monotone convergence theorem, if this function x omega can be defined as the limit over all of these, what are known as simple functions, which are defined by these piecewise constant things, then the area under this full curve is going to be given by the area, the limit of the area of each of these rectangles, which can be defined just by length times height. So this looks like what you might have seen in a calculus class, except rather than taking the points of x omega as the primitives, as we do in a Riemann integral, so we take this point and this point and this point, and then we try and evaluate it at a set of points. We approximate it from below. So rather than sort of, so one way of thinking about this is rather than splitting it up vertically, we're splitting this up horizontally, adding additional components vertically in this monotone fashion. And so this is a way of thinking about how measure theory performs integration. That said, this is not how we calculate most expectations In practice, we have much simpler ways of doing so than by following the axioms. And so what we do is we define a density or a distribution. So let's define what a density is. So we take two measures that I'm going to call mu and nu. It's a Greek letter that looks like a V and is hard to draw in a way that's distinct from a V, but I'll say nu. And so these are measures, they're not necessarily probability measures. We say mu, and then we draw these two arrows and say this mu, this is pronounced as is dominated by nu, or mu is absolutely continuous with respect to nu. If nu of A equals 0 implies mu of A equals 0. So what that means is that for any sets such that the dominating measure nu assigns 0 probability or 0 mass to them, the dominated measure mu also assigns 0 mass to them. So it can take a 0 mass set and turn it into a positive mass set. For any other sets, there's no restriction. So if this doesn't say that the measure of any set is less than the measure of any set with respect to mu is less than or equal to the measure of any set with respect to nu. It requires that only for sets of measure 0 with respect to nu. And so we need one more condition to define this. These are sort of preliminaries. We say a measure mu on a space omega f is sigma finite if omega is the countable union of sets AI such that mu of AI is finite for all I. And so what this is to say that densities are going to be defined for finite measures, so things that assign a finite mass to any set. We can extend that slightly to measures that might assign an infinite mass to some sets, so long as that infinite mass can be broken down into a countable number of finite sets. The idea behind this is that, for example, the real line is infinitely long, but it can be broken down into a countable number of intervals, say 0 to 1 or 0 to 1,000. It doesn't actually even matter how large that interval is, so long as it's finite. And we can completely cover the space with a countable number. And so this then allows us to not have to deal with infinities. And if we have that, we can apply what's known as the Radon-Nikodym theorem. So, which says that let mu and nu be two sigma finite measures, and let mu be absolutely continuous with respect to nu. Then there exists a function, in fact, a random variable, so a measurable function, which we're going to call d mu d nu, which is non-negative, such that the expectation under the mu measure, so recall that each measure on a space induces an expectation of a random variable x, is equal to the expectation under the nu measure of x times this function d mu d nu for any random variable x. And so what this says is that if we have two measures, one that is easy to calculate with, which is generally going to be the measure nu, and for which we can calculate the expectations in some usefully interesting way. And we have another measure mu, which is dominated by it. Then we can calculate the expectation of any random variable with respect to this other measure mu, which might be more challenging, by multiplying the random variable times d mu d nu. And this d mu d nu, so it has the property that it's non-negative, and it has nu measure equal to 1. And so we give this a name. We call this the density of mu with respect to nu. And this is generally going to be the way that we're going to calculate expectations. We may be in many cases simply given the density. So probably in a lot of undergraduate probability classes, you saw densities and they were simply defined as the distribution. In fact, this is not necessarily identical to the distribution, but it uniquely characterizes it. And so this allows you, if you have a dominating measure, to define expectations with respect to a density mu. So sometimes we also call this the radon-Nikodym derivative instead of the density. Again, that's something where measure theorists use the term radon-Nikodym derivative. Everybody else, so outside of this class, unless you're reading a math paper, people will say density. So the proof of this is in the Pollard textbook that I mentioned last class. It's constructive. It proceeds from the axioms. I don't find it particularly enlightening. They simply go step by step, constructing what this looks like for any set of measures. The point of sigma finite is just that, so you want to avoid these things being infinite at some point, because so comparing two infinite objects, it's hard to make a comparison. And then the point of being absolutely continuous, that's also the idea that, so if we take a set of new measure 0, and we try to calculate the mu measure by multiplying by some random variable, 0 times anything is going to be 0. And so we can't, in this multiplicative fashion, get a number that's non-zero if the set is has new measure 0 and mu measure greater than 0. And so that's why the restriction on absolute continuity is needed. And so in practice, rather than sort of going from measures to densities, we'll often go from densities to measures, in the sense that the thing that you will know about is the density, and you can use that to compute the properties of the measure. And so I said that this is going to be helpful for you if you have a dominating measure which is easy to calculate with. I have not yet given you a dominating measure that's easy to calculate with, so let's do that. So consider the case where omega is equal to the real line. Then the measure that's going to be most commonly used here as a dominating measure can use the uniform measure, also called the Lebesgue measure. It's after Henri Lebesgue, who came up with most of these axioms of measure theory that we've been talking about. And so again, we can define this. So the trick in probability theory is you define something over some simple cases, and then the axioms take care of the rest. And so what this says is that, let's call this mu. And so it satisfies mu of the indicator of the set A is less than omega is less than B is equal to B minus A for any A comma B in the real line. And so that defines the indicators of intervals as just the length of those intervals. And so it's defined over a sigma field containing all such intervals. And so these here are the open intervals. I did this with a strict inequality here. But by the principles of the definition of a sigma field, this sigma field must include the complements of these sets. And so in particular, the complement of this is, so it contains, for example, minus infinity to A with this closed. It contains union, so the complement of that set is B comma infinity, contains, as examples, minus infinity to A, union B comma infinity. We can take the intersection with another half open interval, and so we can get sets of with another open interval, so we can get half open intervals. We can again take the intersection of these half open intervals, so it contains sets of the form closed intervals. So this open versus closed doesn't matter, it contains all of them. And so in fact, so this the sigma field contains any open set, any closed interval. So there's some technicalities. So can be defined on the Borel sigma field, which is the smallest sigma field containing all of these. Open sets. Sometimes a slightly larger sigma field. Which contains a few extra sets that are not well defined. Note that so based on this intersection union principle, this contains the singletons. And what we can do with this is we can define the measure of all of these. So by this principle of decomposing things into their unions, so the measure of a closed interval, so of an open interval. So here, let's do this proof this way. Sorry, just a second. So consider so an open interval AB, an open interval BC, and then take the union of these. And so the Lebesgue measure of these is equal to, by this disjointness, is equal to C minus B plus B minus A, which is equal to C minus A. And then consider also the Lebesgue measure of, so the open interval AC. And that's just by the definition of Lebesgue measure, that's also C minus A. And so the difference between these two sets is simply, so A comma C excluding, so this set A comma B union B comma C. The difference of those sets is just equal to the singleton B. And so what this says is that the measure of the singleton B, we can, by taking the sum of the union of the singleton B and this set that excludes the singleton C, that has to add up. And so the measure of B has to equal 0. And so this is sort of a fundamental principle, sort of like the one thing that you learn about Lebesgue measure, which is that the measure of singleton sets is well defined and it's equal to 0. So that extends very simply to any countable union of singleton sets. So any countable union of singleton sets has Lebesgue measure 0. And so what does this allow us to do? Well, so we define this we define for functions, the measure is effectively the area. In fact, the drawings that I was doing, if you assumed that that measure along the line was just the length of the line, then this is just the traditional concept of area. And in fact, measure of x of omega is equal to the integral of x of omega d omega, where the integral is the standard Riemann integral from your high school or undergraduate calculus classes. So this is the one that's defined by, so let me draw a left Riemann integral. You take a partition, a set of points, and then you simply extend the value of the function at that point. To the next one. And so we see here that this doesn't restrict us to staying below the function. And just we take finer and finer partitions and then take the limit. And so for any function that's Riemann integral, so for any function that is both Riemann integrable and Lebesgue integrable. So if it's defined for both, then it's just equal to the same thing. And so any of those rules that you learned for integrals in your basic calculus class still apply. The thing that the Lebesgue integral lets you do is consider a function of the form, so it's a continuous function except at a single point. This eraser needs to be. Let's erase just a single point there. And then say it's differing at this point. And so here's your function. So this is your x of omega. And this is, say, like omega 0, something like that. Now, you can define the Lebesgue integral with respect to this function, because we know that the measure of the singleton omega 0 is equal to 0. And so we know that this integral here, so this is a measurable set, and so the contribution of that to the integral is equal to 0. And then we can define on any of these other points. So on any of these other points, we can define this in the usual way. And for this continuous function, that's going to be equal to continuous bounded function. This is going to be equal to the Riemann integral. But the Riemann integral actually isn't defined, because if you start one of your intervals at this point, omega 0, and try and extend left, then the limit or extend right, the limit you get will be different from if you started no matter how, just a little bit to the left or to the right. And so that limit is not even defined. So the limit as you take the partitions finer and finer of the value at a set of points is not even defined. And so this allows you to integrate a strictly large, well, a set of functions that are strictly excluded from the set of functions that are Riemann integrable. Where you'll most often see this, aside from probability theory, is in when you're dealing with general equilibrium theory or game theory. it will often be stated that you have many agents, many individuals, and the start of the theory section of many papers in general equilibrium theory or certain branches of macro and certain types of game theory that follow this will be, let there be a measure one of agents. This is, so this is probably the one thing that you'll take sort of a decade into the future from this measure theory lecture. You will be reading papers 15 years from now where the unique reference to measure theory is let there be a measure one of agents. The point of that is it tells you that they're working with Lebesgue measure. Each individual point has mass 0. And so when they're calculating something in terms of fractions of agents, when you ask what does an individual count for in terms of that fraction, so what happens if one individual point changes? And the answer is that the total fraction doesn't change. And that's sort of the main result that gets used from measure theoretic probability that's distinct from standard integration. And other than that, you can probably rely on your knowledge of basic integrals. So that's Lebesgue integration. And now this allows us to define a continuously distributed random variable, which is something that is taken often as a fundamental in introductory probability classes. Has a density, which we'll call fx omega, with respect to Lebesgue measure. And so this allows us to compute the expectation of any such variable by using integration. And so we say x is distributed according to f of x, if f of x is the density of x. So we read this tilde as is distributed as. And so we call f sub x the probability density function, or PDF of x. And we can use the Radon-Nikodym theorem to define the expectation of x as equal to the Lebesgue measure. So the expectation with respect to the Lebesgue measure, let's the expectation with respect to Lebesgue measure of x times the Radon-Nikodym derivative, which is f of x. And so this is equal to using the equivalence to the integral, and we'll often use this integral just to mean the Lebesgue integral, as this integral x of omega times f of x of omega d omega. And so this is how you calculate expectations most of the time. So mostly you'll be given or propose some density, and then that will be the information that you need to calculate expectations, probabilities, and so on. Sorry, this is, so the expectation, yeah, that's right. No, excuse me. This is omega here. So this is X takes on value omega here. So this is, that's right. So for each value omega, there's a probability of, there's a probability mass of f of x right here. So that's the formula. Now, the multivariate Lebesgue measure is an extension of this on Rn, is defined similarly. And so in particular, that means that, so the measure of, so let's say A comma B cross C comma D cross and so on. So open rectangles or hyperrectangles is equal to, so B minus A times D minus C times and so on. And so in particular, by the same results, we can say that the expectation of x omega is equal to this multiple integral over however many dimensions this is, n dimensions of x omega d omega 1, d omega 2, so on up through omega n. And so this is just multivariate integration. And again, it's performed similarly to multivariate integration in the Riemann case with these sorts of minor extensions for things like measure zero sets, which aren't defined for Riemann integrals. So example continuous densities, things you might see. Are the uniform density on AB, which is has PDF equal to one over B minus A on the closed interval AB and 0 elsewhere. And so this is basically the restriction. So Lebesgue measure is uniform on the real line. It's not a probability density or not a probability distribution. And the uniform probability distribution basically normalizes this on a particular interval to have mass 1, hence the 1 over B minus A. And so this is the probability of any subinterval of this is just equal to the length, just like for Lebesgue. Additional examples, the standard Gaussian. Let's say the standard Gaussian on Rn is an n-dimensional Gaussian. And this has a PDF equal to 2 pi to the minus n over 2 times e to the omega prime omega over 2, where this omega is some vector omega 1 through omega n. And so this is a radially symmetric bell curve shape density. It's centered at 0. So the PDF looks like along the marginals, it looks like this, except not really. It's a not great drawing. It looks like, looks a bit more like this. Extends out to infinity, decreases at an exponential rate. This is along any axis, centered at 0. And this shows up all the time in probability theory due to some limit results we'll get to probably, if not next class, fairly soon. So it's not necessarily true that everything you find is Gaussian. It will be, in some formal sense, pretty close to true that almost everything that you find is approximately Gaussian if looked at in the right way. And that's going to be due to some limit results which show that many things are well approximated by Gaussians. So that's a density that you'll be finding yourself using very often. So other properties, so the expectation measures the center of a distribution. And so expectations of functions can describe other properties. So as an example, the expectation of a quadratic is commonly used. And so we call this, when it exists, the variance of a random variable x is equal to the expectation of x omega squared minus expectation of x omega. Excuse me. So there's equivalent definitions here. Let me go over them one at a time. So the expectation of x omega minus the expectation of x omega minus the expectation of x omega. So the parentheses here are crucial. So it's x omega minus its expectation squared. And so this is the average squared distance between x omega and its expectation. We can expand that square to, this is the expectation of x omega squared minus expectation of x omega squared is another way of writing this. And this measures dispersion. And so if the variance is small, the distance between x omega and its mean in this quadratic sense is small on average. And so probabilistically, you might say that with high probability mass, this distribution is close to its mean. So that's of course weighted. So if, for example, with low probability but with high value, so if there's a set of probability mass 0.001 on which this distance is 10 to the 500, then that expectation might still be large. So might be on the order of 10 to the 498, even if the rest of the probability mass is exactly at the expectation. And so this is sort of a weighted distance. We can extend this from the quadratic distance to additional ones by defining the kth central moment of x, which is just defined as, rather than the quadratic distance here, we go with the kth power. Note that this isn't necessarily a distance, because for odd numbers, this can be positive or negative. So these have names. If k equals 3, we call this the skewness. If k equals 4, we call this the kurtosis. Kurtosis is always non-negative. Skewness can be positive or negative. You'll learn to recognize distributions with positive skew. They might have a density like this. And distributions with negative skew, they may have a density like this. And then distributions with zero skew are symmetric, because this positive and negative, or let me rephrase that. Symmetric distributions have zero skew, because the positive and negative parts cancel out. Distributions with high kurtosis have a lot of mass in the tails. So they look like, well, whatever. They look like this. And distributions with low kurtosis are highly concentrated at the center. So they might look like this. So very often we'll be making assumptions about the moments of random variables that we cover in practice. So various results apply only under, for example, finiteness conditions on various moments. Often especially, so finite mean is the most common assumption, because we'll want to calculate means. Finite variance will also be useful. Certain results that we'll need that I'll get to fairly soon will rely on finite skewness. Even more strong results can sometimes be obtained under finite kurtosis. Assuming that these things are finite can be sometimes quite challenging, because it says more and more about how rapidly this distribution, the probability of being in a particular large value decays as the size increases. And you'll find often that distributions in, for example, finance appear to be well modeled by distributions where the higher moments, such as kurtosis, are extremely large and may or may not be finite. And so if you're working in finance, you should be very scared when a theorem says we assume the existence of 7 moments or 8 moments or 10 moments. If you're working in other disciplines, you might be reasonably happy with this. Where things are bounded, you don't have to worry about it. So let's do one more useful measure. Which is counting measure. Again, not a probability measure. Mu of A equals number of elements in A. Oh, I should say this is defined on omega finite or countable. If omega is not countable, the number of elements in A may not be well defined, or may not at least be finite. And so we say that we have a discrete random variable. If it has density, we'll call this P again, with respect to counting measure. And we call the density the probability distribution or probability mass function. Sometimes abbreviated PMF. And then just again, using this Radon-Nikodym result, the expectation of a discrete random variable is equal to the expectation with respect to counting measure of x times px omega. And this is equal to sum over omega of x omega times px omega. And so this is just the sum rather than the integral case. Yeah. And so these are sort of the two cases, the discrete case and the continuous case that you see in an undergraduate probability class. And you just define, okay, here's a probability mass function, here's a probability density function. These are simply special examples of measures. And they're dominated by either one of these two measures, the counting measure or the Lebesgue measure. You can have random variables that aren't dominated by either of these measures. For example, you can have mixed, discrete, and continuous random variables. And these are well defined. And you can even define a density for them if you let the dominating measure be the sum of the counting measure on the discrete part and the Lebesgue measure on the continuous part. So there's a lot of things you can do with sort of more general measure theory, counting measure and Lebesgue measure, and random variables which are dominated, which have distributions which are dominated by these measures are the most common applications.
I have a quick question. When could one encounter such an example?
So
discrete and continuous.
A very common case, and we'll actually see this later in the class, is so let's say we're interested in purchase decisions somebody makes of a product. of, let's say it's, you know, a quantity of water. So something continuous. I'm going to buy this many gallons of water. And if we look at the distribution of purchases of water, that distribution will contain many non-negative values, which are potentially, you know, continuous, however many gallons of water. But then many people will also buy exactly zero because they're not purchasing from whatever that seller is. And so there will be a mass, you know, maybe 50% of people will buy exactly zero. And so that distribution will contain a positive probability of a set of zero Lebesgue measure. So zero is a singleton set, has zero Lebesgue measure, but we assign a positive probability. And so this distribution that I just described is not dominated by Lebesgue measure, but it is dominated by the sum of Lebesgue measure and counting measure. Yeah, that's, I think that was a helpful question because going through an example probably made that a lot clearer than just defining the terms. So another way we can define a distribution is, so for x in Rn, a random variable, I'm going to abbreviate that RV because I'm tired of writing, with distribution Px, the sets x less than or equal to little x for x in Rn fully determine distribution if the range is the Borel sigma field. It's defined by such sets, and in general, this will be. So now we're getting away from things that are necessarily dominated by a particular measure on Rn, but we are assuming that they're random variables that map to the Borel sigma field defined over Rn. And for those random variables, whether or not they're measurable, we can always define the, they're dominated by the Lebesgue measure. We can always define the distribution using the push forward, using the probability over the basic sets, over the probability over the sets defining the sigma field. And the sets that define the sigma field over the range space, we can restrict these to these half-closed intervals. The sets x omega is less than little x. And so we get all the information we need.
Excuse me, David. Just a quick question here.
Sure.
Could you please explain a little bit about the dominate? I mean, you said a random variable is dominated by measure, but do we have a definition of what the dominate means?
Yeah, let's, so dominated is a synonym for is absolutely continuous with respect to. Mm-hmm. Here we are.
Oh, yes. Yeah. Oh, I see. Yeah.
And so I said a random variable. So when I gave the definition, I said that a measure is dominated by another measure. And then I very quickly slipped into saying things like a random variable is dominated by a measure. In fact, a random variable is not a measure.
Okay.
Nevertheless, a random variable is associated with a measure uniquely, which is the distribution of that. And the distribution of the random variable then is a measure that can be dominated in this sense by Lebesgue measure.
Okay, thank you.
There's a lot of kind of sloppy language in probability theory, and you'll see me slipping into it very quickly. So for example, I've forgotten to say measurable. I've defined random variables without saying what is the sigma field over which their range space is defined. And in practice, that's often commonly assumed. There are natural choices for all of these things. And they're very often just completely left unstated, even when going through theorems. And that can be kind of challenging at the start. And sort of everything is well defined if you make the sort of natural decisions as to these things that are being left unsaid. But there is sort of an infrastructure there. Okay, so
Okay, thank you.
We've stated now, so X is a random variable. And when I say that, I mean a measurable random variable whose range space is Rn, associated with the Borel sigma field on Rn that's defined in terms of the open sets, and equivalently the half-closed intervals also through this product of intersections and unions to find the Borel sigma field. And so we can define the measure by calculating of the measure defined by X, the push forward measure, the distribution of X, by calculating the probability measure of these sets, X omega is less than or equal to X, for all such sets. And so this is defined along, so each such set is uniquely associated to a single point, which is this value X. And so for each such point, there's a probability. And so this is a function that we call so this is from Rn to, so because it's a probability measure, it's somewhere between 0 and 1. And we call this the cumulative distribution function. Or CDF of the random variable X. And so if F is differentiable, ddx F equals, we'll denote with a little f, is the density with respect to Lebesgue measure. And so this is another way of relating distributions to densities and calculating expectations. So this CDF can be defined essentially axiomatically by simply taking the measurable sets, or the subset of those measurable sets which define through the axioms the entire set of measurable sets that we might be interested in. We can calculate that through a single function. We can represent that as a single function. And so that contains all the information that we might be interested in about the distribution of this random variable. And then we can map this in the case where this random variable is dominated by, has distribution dominated by Lebesgue measure to a density. And that density just takes the form of the derivative of this. So that's another sense in which this Radon-Nikodym derivative is something like an actual derivative, which is sort of where the notation comes from. And so this is another thing to calculate that you can use for calculations. Note that the CDF does not require domination with respect to Lebesgue measure. because this can be non-differentiable or even discontinuous. If it's discontinuous, that indicates that there's a point at which the measure of that point is non-zero of that single point, and we know that the Lebesgue measure of any singleton set is equal to 0. And so in that case, that distribution would not be dominated by Lebesgue measure, and so it would not have a density. So there's an ordering on Rn. And so we can say some other things aside from that f is in less than 1, in less than 1 and greater than or equal to 0, because it's equal to probabilities. So if x1 is greater than x2 in the vector sense, so in the sense that every element of x1 is greater than or equal to x2, then f of x1 is greater than or equal to f of x2. And so this is a monotone increasing function weakly on Rn, is the other thing that we can say about a CDF. Okay. Now, other properties of random variables. So if we have two random variables, so let x1 omega, x2 omega defined on omega f. The distribution of x1 comma x2, the vector, is the joint distribution. There's nothing really fundamental about it. It's just the distribution of a variable that's in Rn. We sometimes denote this p x1 comma x2. And then the distribution of x1, x2 individually are the marginal distributions. And so we can show if x1 comma x2 has density f x1 comma x2 with respect to Lebesgue measure, then fx1 has density given by the integral over x2 of the density of the joint distribution. Likewise, fx2 has density given by the integral over x1. And this can just be done by taking this multivariate integral and then applying, and then applying Fubini's theorem, which says that you can switch the order of the integrands. That said, you've probably seen the Riemann version of Fubini's theorem, that you can switch the order of the integrands. So integral of, so any, let me call this big F, x1, x2, dx1, dx2 is equal to the integral of fx1 comma x2 dx2 dx1 for let's say bounded f. So long as everything keeps finite, you can switch the order. That's true of Riemann integrals. It turns out it's also true under some finiteness conditions for Lebesgue integrals. And so what can we do with this, aside from characterize things? We can define concepts that characterize the properties of the joint relationship. And the most important property that we'll be using repeatedly is independence. So we say x1 comma x2 are independent if the expectation of f of x1 times g of x2 is equal to, where this expectation is taken with respect to the joint distribution, is equal to the product of the expectations of f of x1 and g of x2 with respect to the marginal distributions for any fg where by for any, I of course mean any measurable fg that are defined over the corresponding spaces. So if densities exist, independence is equivalent to f of the joint density, f of x1 comma x2, x1 comma x2, being equal to the product of the marginal densities. So this extends to greater than 2 variables. And the interpretation is that it says that x1 provides no information about x2 or vice versa. And in fact, this can be made formal in the sense that we can describe independence in terms of the random variables. These random variables are defined in terms of measures. We can also talk about sigma fields being such that random variables on these sigma fields are independent. And so hence this is a statement about a relationship between information sets. Nevertheless, it's easiest to work with this sort of characterization in terms of expectations of random variables. So the next thing, and I'm roughly where I want to be, is something that we're going to use to characterize the relationship between random variables, is to describe conditioning. And so I'm not going to describe conditioning in full generality. It turns out that there are a lot of technicalities there in defining relationships between random variables in terms of conditioning. There are axiomatic treatments of it that are sometimes needed to deal with cases of measure zero sets. And there's some sort of fun mathematical paradoxes if you're into that kind of thing. that led to the requirement of an axiomatic characterization of what conditioning is. Nevertheless, in this class and in most of what you're going to see, we're not going to need the axiomatic characterization, and we can rely on a characterization defined in terms of densities, which again, so a density is not the same as so density need not exist in all cases for a measure, but when they do exist, they tell us everything we need to know about the distribution. And so in the case where they do exist, conditioning is fairly straightforward. So again, let x1, comma x2 be a vector valued random variable with density f sub x1 comma x2. Then the conditional density of x1 given x2 is, we'll denote this with a bar for conditioning. So x1 bar x2, f of x1 bar x2 of x1 bar x2 is equal to f of x1 comma x2 x1 x2. So the joint density divided by the marginal density of x2 when this exists. And so if the density is strictly positive for x2, the marginal density for x2 is strictly positive, then we define the conditional density as this ratio of the joint density to the marginal density, which recall we can define the marginal density just in terms of the integral here. So for cases where this density is zero, where the density, the marginal density of x2 is 0, it's conventional to say that the conditional density of x1 given x2 is also equal to 0, so that we're not dividing through by 0. But in general, it's just undefined. And so this gives us a conditional expectation. So the expectation of g of x1 given x2. So this is like the expectation notation that we had before, except there's a bar here, which is equal to the integral of g of x1 times the conditional density. And so the sense in which this is like a density is that you take the product of the conditional density times the function of which you want the expectation. And that gives you this conditional expectation. The difference here is now this is not simply a real number, but this is a function of x2, which is itself a random variable, and so is a random variable. And so the most useful property, and we'll be using this extensively, is the law of iterated expectations. We're going to be using this so extensively that I'm going to use an acronym, the LIE. I'll write that after the lines of a lot of steps in theorems. That step will be true, but we will be using this acronym. And the statement says that because this is a random variable, the conditional expectation is a random variable. We can take the expectation of that random variable with respect to the distribution of x2. Yeah. Oh.
Sorry.
And this is just going to be equal to the conventional expectation of g of x1 for all g. So further, if we have, so f of x2 times g of x2 times g of x1, then conditional expectation. So the expectation with respect to x2 of the conditional expectation of f of x2 times g of x1 given x2 is equal to conditional expectation of x2 of f of x2 times the expectation of g of x1 given x2. So we can take the any function of x2 outside of the conditional expectation. It's constant with respect to this function x2. So holding x2 fixed, we can multiply that out. And then this again is equal to, so we can pass through the law of iterated expectations, and this is just equal to, so the joint f of x1, g of, sorry, f of x2, g of x1. And so in the axiomatic definitions, they actually start here and move back to the density characterization. If you start with the density characterization, you can prove this by simply noting that the integral of this density right here times the marginal density of f of x2 just cancels this term out and you get the joint density. And so the product of this and the marginal density is the joint density, and that gives you the law of iterated expectations by just passing inside the integral. So another fact about this is if x1 and x2 are independent, then the conditional expectation given of g of x1 given x2 is equal to the expectation of g of x1. And so this unconditional expectation is equal to the conditional expectation. Now, this is a little weird because the thing on the left is a random variable. And this thing on the right is simply a real number. And so in fact, the proper statement of this is, so this equality is, so we say almost surely for this inequality, for this equality. And so that what that means is that, meaning, so the probability that these two things are equal to each other. Because the first is a random variable. And so it has a probability equals 1. And so again, this can come from the factorization definite property of independence. So if these factorize, so if x1 and x2 are independent, then f of x1, x2 is equal to the product of f of x1 times f of x2, and then dividing through, we get f of x1. And so that's the density of f of x1. I believe we're over time, but we're done with the probability, the pure probability theory section of the class. So you can either be disappointed or breathe easily. And next class, we'll get into statistics and asymptotic theory.